To effectively understand the topic of copula generation in the later sections of this course, it is essential to first grasp what a copula is, or at least develop an intuition about it. Since we will be discussing the generation of copulas from two-dimensional copulas, I will first illustrate what a two-dimensional copula is. For this purpose, I will use a scatter plot displaying blue dots. Now, suppose we have a two-dimensional random variable x1, x2. We can observe its realizations, meaning the individual points x1, x2. If we know or can identify the marginal distributions of x1 and x2, denoted as f1 and f2, we can transform the points x1, x2 through these marginal distributions into new points u1, u2. These transformed points u1, u2 correspond to the blue dots on the scatter plot. The points u1, u2 have coordinates within the closed interval from 0 to 1. For these points, we can determine a certain function, called a copula, which satisfies the properties stated in Sklar's theorem. This function is commonly denoted by a capital C. On the left panel of the visualization, we can see the function c of u1 and u2. The points u1, u2 are obtained via the marginal distributions and are counterparts of the points x1, x2. Thus, we must choose the function c in such a way that it best approximates the values of the joint cumulative distribution function f at points x1, x2. This is shown on the left panel, where we have the copula CDF. F of x1, x2 should ideally be equal to c of u1, u2. The functional form and parameters of the function c must be selected so that c can replicate the values of the joint cumulative distribution function of x1 and x2. A well-fitted copula, which encodes the dependency structure between the variables, allows for the computation of various probabilities, both joint and conditional. The marginal CDF values for x1 and x2 correspond to the values of the copula when one argument equals 1 and the other is u1 or u2. For instance, the value of the copula at 1, u2 equals u2, which corresponds to the marginal cumulative distribution function of x2, where the CDF equals u2. Now, let's move on to the copula density function, PDF, known as the copula probability density function. It is denoted by a lowercase c. This function is defined as the mixed second-order partial derivative of the copula CDF, which is visible in the left panel. However, this function does not have the same direct relationship with the joint density function of x1 and x2 as the copula CDF has with the joint CDF of x1 and x2. The two-dimensional density of the random variable x1, x2 is expressed in terms of the copula PDF, but is not equal to it. Instead, the joint PDF of x1, x2 is given by the product of the copula density and the marginal densities of x1 and x2. To summarize, a copula is a function designed to replicate, as accurately as possible, the joint cumulative distribution function of some random variables, meaning that C aims to replicate F. Of course, this replication is never perfect, but the goal is to make it as close as possible.